Alright, hi there everyone. Welcome back to another episode of CS 341 Algorithms. This is the third lecture where we're going to be diving into reductions. So what's a reduction? Well, it's a way of taking one problem and solving another problem using a solution to the first problem. And so you all kind of intuitively do this, I'm sure. When you're programming, why would you reinvent the wheel when you can reuse solutions to problems that you've already solved and use them to solve, more complicated problems that are related. So let's jump into an example problem. We're going to look at the two-sum problem. So we're going to come up with some explicit solutions to two-sum, and then we're going to reduce another problem called three-sum to the two-sum problem so that we can use our solutions to the two-sum problem to solve the three-sum problem. Okay, so the input to the two-sum problem is an array of integers, n integers, a1 up to an, and a target integer t. And the output of two-sum is true if there exist two values in a, they could be the same value, whose sum equals the target t. Otherwise, the output is false. So the question is, in this array of integers, can I find two integers, ai and aj, where j might be the same as I, such that the sum ai plus aj equals t. Okay, and the output to this problem is true-false. And so this is known as a decision problem because the job of the algorithm is to decide if the correct output is true or false. Here's an additional definition. We have problem instances, which are inputs, right? So an instance is, the array A and a target T. And a particular instance would be a particular array and a particular target T. So for example, the array 1, 2, 3 and the target 5 would be a particular problem instance. And a yes instance is an input to a decision problem for which the correct output is true. A no instance is, of course, an input to a decision problem where the correct output for that problem instance is false. Okay, so these terms will come in handy throughout the course, especially in the latter half of the course. Decision problem, yes instance, and no instance. And also, reductions. Not everyone teaches reductions early on in a third-year algorithms course at Waterloo, but I think it's been becoming more common in recent years, or at least I've been more aware of it in recent years, because reductions are something that are absolutely vital for understanding the complexity of problems and relating the complexities of different problems. And so this will be really useful when we get to, intractability and the complexity of problems section in the, let's say, the last third of the course. And it's really easy for reductions to appear really mysterious and magical if we introduce them at the same time as intractability. So I favor these days introducing reductions early in the course so you can start to wrap your mind around them and make sense of them, without all of the added complexity of thinking about problem classes and intractability classes and tractability classes and so on. Okay, so this stuff we're going to cover in this lecture will largely be used in the last third of the course, but let's look at it now and try to understand it gradually over the process over the duration of the course. Okay, so a simple brute force solution to the two-sum problem, I'm sure, is something any of you could have come up with in 60 seconds. If we want to find two indexes, in the array that sum to t, whose values sum to t, just use two for loops. So we go for I equals 1 to n, for j equals I to n, and there's no need to explore any j values smaller than I because of symmetry. Exploring j values smaller than I is really the same as exploring I values smaller than j, right? And then, once we find two array indices whose contents sum to t, we're done and we return true. If there's no such pair of array indices, we return false. Okay, this is the trivial brute force solution to this problem. And the runtime for this problem is, order n squared. It's theta n squared by, arguments that are, stuff we saw in the last lecture. Now, what if we want to come up with a more efficient solution to this problem? let's try to turn the innermost loop perhaps into something more efficient. And in fact, you might want to pause here for a moment and see if you can solve this problem yourself. How could you implement this more efficiently by replacing this inner loop with something else? So I'll give you a moment to pause. I'll take a sip of my coffee. Colombian roast. Okay, so I'm going to assume now that you've done that if you wanted to do that. There's a pretty straightforward way of doing this. So we can replace a single loop where we search for a couple of array indices with a particular value. Really, we're iterating over the j, looking for something that will match this expression. So this is a search problem, right? And to search more efficiently than linear search, we have, binary search, right? At least in a sorted array. So, okay, we could sort, and sorting takes n log n time, and we could still hope to get n log n time after that sort, which would be asymptotically better than the n squared that we saw in the brute force solution. So here's an improvement. For a given slot a of I, if we want a of I plus a of j equal to t, we can just rearrange to get a of j equal to t minus a of I. So this tells us what we're searching for, the a of j that we're searching for. And instead of looping over j, we'll just do a binary search over the array for t minus a of I. And of course, this search, to do it efficiently, well, I've already given the solution here. It's binary search. So versus linear search to take linear time, binary search will of course take order log n time. And of course it needs the elements to be sorted. So here's our improved algorithm. We're going to sort the array A, then we're going to iterate over all of the I values we could choose from 1 to n, and we're going to do a binary search to get our j value, looking for t minus a of I in the A array. And if this search is successful, we're going to return true because we found two indices, a of I and a of j, that sum to t. Otherwise, we're going to return false. And I want to remind you that I and j could be the same index. So what's the time complexity of this algorithm? And you can try to answer this yourself if you want, pausing. I'll give you a moment to pause. Okay, real quick one. I'm going to assume you've paused, and let's go through the time complexity. So, everything's out of order. Oh no. Well, I don't want to re-record this, so here's our algorithm, and you can see that the sort step, of course, is theta n log n time, assuming we use a comparison-based sort. And then we have theta n iterations of this I loop, and then the binary search does theta log n work. So our loop is going to contribute the number of iterations times the work per iteration, which is theta n times theta log n. We get theta n log n. And then, of course, we have the n log n sort at the beginning. So the entire algorithm is an n log n sort, followed by n log n for all of the work done in this I loop. And that, of course, is equal by one of the max rules I mentioned in the previous lecture, to just theta of n log n. Okay. Now, that sort that we did to enable a more efficient algorithm is an example of pre-processing. So pre-processing is something that you do once to modify the input at the beginning of an algorithm to admit a more efficient algorithm, in this case binary search as opposed to linear search. And this is a theme that you'll see come up in a lot of algorithms. Oftentimes some clever pre-processing enables you to compute everything much more efficiently. Okay, so that was the two-sum problem, and at least a reasonable solution to the two-sum problem. We came up with an n log n time algorithm. And the three-sum problem is quite similar. So we have an array of integers and a target t. The output is true if there exist 3 values in A whose sum equals t, and is false otherwise. So two-sum is, well, as you might expect, two-sum is 2 values and three-sum is 3 values. Just like in two-sum, where it could have been 2 of the same value, in three-sum it could be 2 or 3 of the same value. That's fine. So you can pick the same value 2 or 3 times. In other words, we're looking for a of I plus a of j plus a of k that sum to t, and there are no restrictions on I, j, and k. Okay, so this is really similar to two-sum, and whenever you see a problem like this, suppose we have a solution to two-sum and we want to solve three-sum, when we can see that this problem is very similar to two-sum, you might think, well, can I just use my solution to two-sum to solve this problem? It's natural to ask that question. So this brings us to the notion of a reduction. Suppose we already have a solution to 2-sum called solve 2-sum. I'm going to explain what it means to reduce the 3-sum problem to the 2-sum problem. I'm going to do this as an example, and you can infer what reductions are from this example. So suppose we design an algorithm called reduce 3-sum to 2-sum that solves 3-sum. Okay, this is a solution to 3-sum. So I could have called it solve 3-sum, but I'm calling it reduce 3-sum to 2-sum just as a cue to suggest that it's going to use a solution to 2-sum, an algorithm called solve 2-sum, as a subroutine, right? So this algorithm, reduce 3-sum to 2-sum, it's going to solve 3-sum, and it's going to do so by using solve 2-sum as a subroutine. And solve 2-sum in this case, it's a black box subroutine where our reduction here doesn't know how solve 2-sum is implemented, and from the perspective of our reduction, we call this function an oracle. This is a black box subroutine you can call that solves the problem you're reducing to. We're reducing to 2-sum, so we have an oracle that solves 2-sum, and we're going to use that as a black box subroutine. So here's a candidate for this is sort of the template that our reduction would follow. We have reduce 3-sum to 2-sum that takes as its argument an input to the 3-sum problem, because remember, it's solving 3-sum. So it takes an input to 3-sum, and then it does some sort of pre-processing to transform that 3-sum input into a 2-sum input, because we're going to use our solution to 2-sum to solve this problem. You're going to pass that input to 2-sum to our 2-sum solver, and our 2-sum solver is going to return a value that we're then going to return. This is one possible template for a reduction from 3-sum to 2-sum. There are other ways to do this to do reductions, but we're showing one particular template for a reduction here, where we take an input to 3-sum, we process it into an input to 2-sum, and then we solve that 2-sum input. And the way that we constructed this 2-sum input should be very careful and clever. We should construct this 2-sum input so that solving 2-sum here gives us the solution to 3-sum. So reduce 3-sum to 2-sum, our reduction, that's called a reduction from 3-sum to 2-sum. And note that we could also process the input to 3-sum in a different way and then call solve 2-sum multiple times, right? In this case, we're just calling solve 2-sum once, and that's a particular type of reduction that I'll talk about at the end of this lecture. If 3-sum can be reduced to 2-sum, meaning if we can actually solve 3-sum using the output from 2-sum like this, if we can transform the input to 3-sum, so it's an input to 2-sum, and then use the solution to 2-sum to solve 3-sum, then we say we can reduce 3-sum to 2-sum in that case, and we denote this reduction by this less than or equal to symbol. We say 3-sum reduces to 2-sum. That's how we read this. 3-sum reduces to 2-sum. And the mnemonic here, if you want to remember this, is the solution to 2-sum. This is like an arrow, right, pointing to 3-sum. The solution to 2-sum goes into 3-sum. So 2-sum, arrow, 3-sum. 2-sum goes into 3-sum as a subproblem, right? The solution to 2-sum goes into 3-sum, and we solve it using that solution. Okay. So how can we use solve 2-sum? So that was sort of running through what it means to have a reduction, what a reduction from 3-sum to 2-sum would look like. Let's actually try to come up with a reduction from 3-sum to 2-sum. So a reduction from 3-sum to 2-sum is going to use a solution to 2-sum as a subroutine. So we have access to solve 2-sum. How could we use that to solve 3-sum? So we have the power to find two numbers in an array that sum to a particular target. How could we use that to find three numbers in an array that sum to a particular target? Could we transform, so we have this input to 3-sum, which is an array at a target t. Could we transform that input, we process that input to feed it into 2-sum somehow? Well, should we change the array somehow? Should we change the target somehow? And, well, if you want, you can pause here and think for a moment about how you might try to take advantage of this subroutine to solve 3-sum. I'm going to assume now that you've paused if you wanted to do that. And here's one approach to doing this. We iterate for I equals 1 up to n, and we compute a new target where we take the old target and subtract a of I, sorry. So why are we doing this? Well, we're looking for 3 elements that sum to t, and we've picked one of these elements, a of I, as a candidate to be part of that sum. So we want 2 more elements that sum to t minus a of I. We use solve2sum to check if there are 2 such elements. If there are, we return true. If we get through all of the possible a of I values and we can't find 2 other numbers that sum up to t minus a of I for any of those I values, we return false. Okay, so let's see how this algorithm works. We'll just walk through an example. So here's our A array. Suppose we're looking for a target of 9, and let's just take a moment and stare at this array to understand the example. The only way that I can pick 3 numbers to sum to 9 here is if I pick this number 3 times, right? Because everything else is smaller than 3. Okay, so let's see what the algorithm does. First, we'll set I equals 1, and we'll compute our new t2 value, which is going to be 9 minus this array element 1, which is 8. So we're going to run solve2sum on a of 8. Can we find 2 numbers that sum to 8? No, so this is going to return false. In the second iteration, our t2 value is 9 minus negative 7, which is 16. Can we find 2 numbers that sum to 16? No. In the third iteration, we have t2 equal 11. There are no 2 numbers that sum to 11. In the fourth iteration, t2 is 9. There's no pair of numbers that sums to 9. In iteration 5, t2 is 7. There's no pair of numbers that sums to 7. In iteration 6, finally we get to this slot. And t2, oh no, sorry, I skipped one. So in iteration 6, we're on this slot with negative 1, so 9 minus negative 1 is 10, and we can't find 2 numbers that sum to 10. Finally, in iteration 7, we get to this slot where a of 7 is 3, so 9 minus 3 is 6. Can we find 2 numbers that sum to 6? Yes, 3 and 3, so solve2sum a6 will return true, and we will thus return true here. Okay, so that's an example of how that works. Let's talk about how you would argue that a reduction like this is correct. So what we want to prove is that for a particular instance, a t of 3sum, it's correct for 3sum to return true if and only if there is some index I such that it's correct for 2sum to return true on input / instance a, comma, t minus a of I. Okay, so we're saying consider the instance a comma t that we have for the problem 3sum. Think about how we're going to transform it. We're going to transform it such that it becomes an instance of 2sum a comma t minus a of I. We're going to try a whole bunch of different ways of transforming it, one for each value of I. There should exist some instance that we feed to 2sum that causes 2sum to return true if and only if it's correct for 3sum to return true on this problem instance a of t, a comma t. Okay, in other words, let a comma t be any input to 3sum. There exist ai, aj, ak that sum to t if and only if there exists some am such that solve2sum a comma t minus am returns true. This is what we want to prove, okay? And by the way, in doing so, we're assuming that our solution to 2sum is correct. So we assume there's a correct solution to 2sum in this. So solve2sum is behaving correctly when we say that there exists some am that causes this to return true. Okay, so we've talked about what we want to prove. Let's actually prove it. So we want to prove, I'm going to prove a set of equivalences, right? With an if and only if, you could do both directions individually. I'm going to do both directions at once by giving you a set of equivalences. So there exist I, j, and k such that a of I plus a of j plus a of k equals t if and only if there exist I, j, k such that a of j plus a of k equals t minus a of I, right? I'm just rearranging this expression. These two expressions are equivalent, right? And that's equivalent to saying there exists some I such that solve2sum a t minus a of I returns true. Okay, because I could argue this point in detail, but you might want to just work out the details yourself. Let me try to walk through why this last equivalence is true. This is maybe where just breaking it down into the two directions is instructive, even if, this equivalence, it's questionable whether we actually need this detail, but anyway, let's break it down into the two directions here, just to try to grow our understanding. So on one hand, if there is an I that causes solve2sum a t minus a of I to return true, that means that there are two values, aj, ak in a that sum to t minus a of I. Okay? aj, ak that sum to t minus I. That's exactly this expression up here, right? And for the opposite direction, if there exist I, j, k such that you have these two values that will sum to t minus a of I, then there will be an I that will cause solve2sum t minus ai to return true. Okay, so hopefully that makes sense. It's sort of this last step is almost in the realm of just proving trivialities, so it's hard to restate it in a way that elucidates without just confusing you. Hopefully what I've said here wasn't confusing. Okay, so that was reduction correctness. And we'll see a couple more examples of reduction correctness in this lecture, so don't worry if you didn't get the first one. Hopefully the concepts will continue to make more and more sense with each passing example. How do we talk about the runtime of this reduction? Well, if you look at the runtime of this reduction, you've got a loop with theta n iterations. You've got work done by each iteration that is a constant amount of time for this step at line number 3. And then line 4, we're invoking solve2sum. So really this expression is going to depend on what the runtime of solve2sum is. And there are, of course, many different ways that you could solve 2sum. And so the runtime is going to be dependent on that implementation. We can say this reduction adds theta n overhead beyond whatever this runtime costs in some sense, but the expression is a little bit more complicated than that because we have this invocation n times in this loop, right? So really, when we want to talk about the runtime of this reduction, the runtime is going to be n times the runtime of solve2sum. Now, for our brute force solution of solve2sum, that was an n² solution, a theta n² solution. We end up with theta n³ runtime. But for our more efficient 2sum solution, we can get theta n iterations times theta n log n runtime for solve2sum, which is theta n² log n. So, okay, we can solve this problem in n² log n. Can we do better, though? Well, recall that our fastest solve2sum solution we've seen so far, it had a sorting step that took theta n log n time, and then the searching step took theta n log n time over all the different I values, right? Because for each I value, we were doing a theta log n search. Now we can actually improve 2sum's searching time to theta n time total, not theta n log n time over all the searches, but theta n time total, so linear time. And then that would leave us with this sorting time we have to contend with still. But anyway, we can improve the searching time. And it turns out that improving the searching time is actually enough to come up with a new 3-sum reduction that's faster. So let's see how we can come up with a 2-sum algorithm that's even faster. Okay, so here's an example input instance where we're looking for a target sum of 23, and we have this array A. Let's see, how could we come up with 23? Well, this 3 and this 20 would work for us, right? So I'm going to show you an algorithm visually, and it's quite simple. We're going to start out with basically 2 pointers into the array. There's or 2 indexes that we're slowly modifying as we iterate through the algorithm. So we're going to start with 2 indexes, I and j, which start at the left and right endpoints of the array respectively. And then at each step, we're going to look at the sum that we get by taking a of I and a of j. And if it's too large, we're going to either increment I or decrement j. Okay, so if it's too large, we're going to move j, right? We're going to shrink j so that our sum gets smaller. This is a sorted array, okay? So we're going to start with our array the same way that we did in our previous 2-sum solution with binary search, but now we're going to do something iterative instead of binary search. That's going to take linear time. So if the sum is too large, we're going to move j to the left, okay? And okay, what's the sum now? It's 22. Well, in this case, we're going to increase the sum by moving our I to the right. So it's too small, move I to the right. What's the sum now? It's 23, and that's just right. Now, if I and j end up meeting and we haven't satisfied, we haven't found the sum we're looking for, then my claim is that there's no solution, there's no pair that sum to the target t. Okay, now if you want to argue the correctness of this algorithm, here's the invariant, the loop invariant that you would prove as you're adjusting I and j in turn. You would prove if there exists a solution I prime where I prime is less than ij, then I prime is greater than or equal to I, and j prime is less than or equal to j. In other words, we haven't passed the I that we're looking for. We haven't passed the j that we're looking for. Okay. And as an exercise, you can try to fill in the proof details here. Okay, so now that we have this faster two-sum algorithm that only takes linear time for the search, how can we use that to build a faster reduction? Well, we still have the sorting cost, right? And so the faster two-sum is not really any faster if you have to sort every time we invoke two-sum. But remember, we're invoking two-sum many times in our three-sum to two-sum reduction. But we don't need to sort every time we invoke two-sum because the array is the same every time we solve two-sum. It's just A. It's not like the array is changing every time we invoke our solution to two-sum. So we can sort the array once at the beginning of our three-sum to two-sum reduction as part of our pre-processing of this input into a two-sum input. So we sort the array, and then we're going to iterate for I equals 1 to n, picking candidate A of i's, and we're going to use our faster linear time two-sum algorithm to look for a solution to see are there two other elements that will sum to t minus A of I. So we can find three elements that sum to t. And this is our reduction. It's basically just plugging in a faster solution to two-sum and then making this observation that we only need to sort once. So our faster two-sum can really be linear time instead of n log n time every time we iterate through this loop. Okay, so what's the total complexity of this algorithm? Well, we have a loop here for I equals 1 to n. And for each of those iterations, we're doing linear time inside the loop. So this is n squared time, and then the sort at the beginning is n log n. So n log n plus n squared is just order n squared times. So this is a theta n squared time three-sum algorithm. And for many years, we didn't think that we could do any better. We thought this was probably an optimal algorithm. But it turns out faster algorithms actually appeared in 2014 and 2017. Right now, the best known solution is order n squared times some crazy polylog factor here, so that this is a polylog factor faster than order n squared. So this is asymptotically, asymptotically subconstant, right? But this is also a kind of a really convoluted expression that's hard to understand, right? So what is log n to the constant over log squared n? Gross. I mean, you could understand this. You could actually try to relate this yourself, these two, the top and bottom of this expression yourself using the limit method, for example. But this is non-trivial to understand if you haven't seen these sorts of functions before. And you always get these sort of weird polylog expressions as a problem is sort of getting close to the point where an optimal solution is known. And the appearance of these horrible polylog factors is a result of an algorithmic process for optimizing lower bounds and upper bounds that's often referred to as log shaving because you're trying to shave off little polylog factors. And we suspect that there's no solution that's faster than order n squared n to the 2 minus a constant. So the question is, can we get order n to the 2 minus a non-constant factor? Probably not. But maybe not. This is an open question. Well, what's this? Time for a silicone break. That was a nice break. Back to the grind. Okay, so let's go through some harder examples. I'm going to go through a few progressively hard, well, I'll start with an easy one, then I'll go through some progressively harder worked examples. So let's start with a trivial reduction. At least it's trivial once you know this algebraic identity. So suppose we want to multiply two integers x and y. Okay, so this is the problem we're trying to solve, multiplication of two integers. There's this identity from algebra, which is xy equals x plus y squared minus x minus y squared all over 4. And now, if you can solve this right-hand side without multiplication, then you can solve the left-hand side without multiplication, right? So you can solve multiplication by reducing it to the problem of adding, subtracting, dividing by 4, which is really, in binary notation, bit shifting to the right by 2, and then squaring, right? So really, we're reducing the problem of multiplication to the problem of squaring, okay? So this is the reduction that we're trying to show. And here's a reduction to do that. So reduce multiply to square takes two arguments, x and y, that are integers, and it relies on addition, subtraction, bit shifting, and then this compute to square function. So we'll assume that addition, subtraction, and bit shifting are all things that we know how to do as base primitives, and then compute to square is the oracle that we're reducing to. Okay, so compute square solves the problem of squaring two integers, or sorry, squaring an integer. Okay, so the oracle gives us a solution to the subproblem, and if we can solve compute square, clearly we've solved multiply because of this algebraic identity. Okay, so that's a really trivial reduction. Here's a sort of medium strength reduction that's a little bit harder. Suppose we have a problem that's related to 3-sum. It's just a little variation on it. So 3-sum, you take an array of integers and a target t. 3-sum 0, you just take an array of integers as input. And the output is true if there exists ijk such that these three a of I, a, j, k sum to 0, not to a target, but to 0. So it's kind of like a version of 3-sum where the target is fixed to 0. Otherwise, you return false, okay? And this is a really similar problem to 3-sum, right? You might wonder, certainly solving 3-sum 0 using 3-sum is really easy, right? If we wanted to solve 3-sum 0, where we only have as input the array A, and we wanted to use as a subproblem a solution to 3-sum where we're allowed to give it a target, we could just give it the target 0, and that would be just a trivial solution, right? But what if we want to go the opposite direction? What if we've solved 3-sum 0, so we can find three elements that sum to 0? We can determine whether there are, we can decide whether there are three elements in the array that sum to 0. Can we then figure out if there are three elements that sum to a target t? So we want to solve full-blown 3-sum with a target. We want to use as a subproblem a solution to 3-sum 0. Okay, so it's straightforward to take a solution to 3-sum 0 and modify it to solve 3-sum, because there'll be, in the code, there'll be, it'll be pretty easy to see how you're searching for something that for three elements that sum to 0, and it'll be easy enough to modify it to search for three elements that sum for t, most likely. But if we don't want to modify the code of 3-sum 0, if we just want to use it as a black box, can we find a reduction from 3-sum to 3-sum 0 that will allow us to reuse as a black box the code for 3-sum 0 without modifying it? Okay, so given an oracle that solves 3-sum 0, let's solve 3-sum. In other words, can we find a sum of three elements that three elements that sum to t by finding three elements that sum to 0? Okay, so I'm going to walk you through a sequence of equivalences that basically imply immediate correctness for the reduction. So suppose that we're looking for three elements that sum to t. There are three elements that sum to t if and only if there are these three elements minus t that are altogether equal to 0, right? This is just algebra. And we can do something sort of funny here. We can multiply both sides of this equation by 3, okay? And you'll see in a moment why I do this, perhaps, although this step certainly looks like magic. So the reason I'm doing this is I want to incorporate this t into all three of these a expressions. I want to sort of be able to group these expressions into something times a minus t. And so I want 3 copies of t to do that, since t is an integer, and I don't know if it's divisible by 3. But I do know that 3t is divisible by 3 and remains an integer. So I'm going to multiply both sides of the equation by 3, and now I can group into 3 expressions on the left, 3a of I minus t, 3a of j minus t, 3a of k minus t. I've just grouped this expression differently. I've parenthesized it differently. Okay, and these are all equivalences, right? This first expression is equivalent to this last expression. So what this tells me is, if I can find 3 terms that sum to 0, where the 3 terms are of the form 3a of I minus t, 3a of j minus t, 3a of k minus t, and I can find those 3 terms that are equal to 0, that's equivalent to finding 3 terms that are equal to t. Okay, so now how can I plug an input sort of this form, where I'll be able to find these 3 terms, into a solution to 3 sum 0? Well, this equivalence, this first row being equivalent to the last row, suggests the following approach. We're going to reduce 3 sum to 3 sum 0 by taking our initial array A and our target T, and producing a new array B, where each cell of this array B is going to be the corresponding cell in A multiplied by 3 and less T. So we're going to take each element of A, multiply it by 3, subtract T, and make that B. And now if we can find 3 elements of B that are, of course, of this form, 3 times some element of A minus T, and we can find those 3 elements that sum to 0, then that's equivalent to saying there are 3 elements, AI, AJ, AK, in the original array A that sum to T. Okay, so solving this problem is equivalent to solving this problem. So return solve 3 sum 0 of B is going to give us our answer. And I'll leave it to you as an exercise to prove formally that this is a correct reduction, but really it follows almost immediately from this set of equivalences. So here, just to reinforce this pattern in your mind, we're pre-processing the input to create a new input to the subproblem, right? And the input to the problem can look quite different from the input of the subproblem, right? This is 2 arguments as input, this is 1 argument as input. We're sort of merging the argument T into this single argument input for 3 sum 0. And then we're going to use the oracle to solve the subproblem, and if this reduction is correct, then the result should be a solution to the overall problem 3 sum, the outer problem that we're trying to solve using the inner subproblem. Okay, so here's our hard reduction. We're going to go from a problem called 3-array 3 sum 0, and we're going to try to reduce this to another problem. So what is this problem, first of all? Well, we're going to take not 1 array of input integers, but 3 arrays, A, B, and C. And the output is going to be true if there exists AI, BJ, and CK. So notice these indices are coming from the 3 different arrays whose sum equals 0. So we want AI plus BJ plus CK to be equal to 0. If there is such a triple, then the output is true. Otherwise, the output is false. Now, this is a little bit different from the other 3 sum problems that we found, right? But we'd actually like to try to reduce this to 3 sum 0. Remember, 3 sum 0, the sum equals 0, and there are 3 elements from the same array. Here we have 3 elements from 3 different arrays. So this problem is going to involve encoding somehow this additional constraint that 1 element has to be drawn from each of these 3 arrays, despite the fact that we are passing only a single array to 3 sum 0. So this problem is an example of, I think it's our first example in this course, of reductions that are much more creative. So it turns out that the sorts of reductions that we're going to care a lot about in the last third of the course are going to involve really a lot of creativity, where we're relating problems that are in fact quite different from one another and that require substantial transformations of the input into completely different types of inputs. You know, for example, some algorithms transform graphs into matrices that we do fancy math on, or encode logical formulae as graphs and then express the solutions to logical formulae as like whether or not you can do a bipartite matching. So there's a lot of room for really sophisticated, creative reductions. And this is going to be our first, just dipping our toe into the vast ocean of complex reductions that have been put together by various people. Okay, so anyway, let's just try to do a reduction from 3-array 3-sum 0 to 3-sum 0. Okay, so it's going to be something like this, right? We need to take the 3 arrays somehow and turn them into 1 array so it can be fed to 3-sum 0, solve 3-sum 0. Now, you might just try concatenating the 3 arrays, right? So concatenate them into a single array, A prime, and then pass that to solve 3-sum 0 and see what happens. Well, is this reduction correct? The problem is that solve 3-sum 0 in this case might choose 2 or more elements from the same subarray. So 2 or more elements from A or 2 or more elements from B. Okay, so let's see how this would actually work if we were to run this algorithm. Well, in this particular problem instance, there's no correct way to get a zero sum. You can't pick one element from each of these 3 arrays and get a zero sum. Because if I pick one element from this, even if it's the smallest element, because there aren't that many negative numbers in this example, right? So if I pick 3 as the smallest element, 4 as the smallest element, there's no way to get a 0 by picking a single element from here. I mean, we could pick 2 elements from A and 1 element from B, like -2, -1, and 3, and we could get a 0, but that wouldn't be a correct solution. Unfortunately, this try reduce 3-array 3-sum 0 to 3-sum 0, wow, that's a mouthful. This reduction attempt will actually find that incorrect solution because concatenating these arrays does nothing to distinguish between them. These are really the subarrays, A, B, C, and this quote-unquote solution, really a solution attempt, will unfortunately find these 3 numbers. When we call solve 3-sum 0, these 3 numbers will be selected and will return true, even though it's clearly incorrect for us to return true in this case. So this is not a correct reduction. And really, this is where the creativity in this problem comes in. How do we prevent picking 2 or more elements from a subarray? And feel free to pause and think about this. But full disclosure, when I first thought about this problem, I couldn't come up with a way to do this, at least in the 5 minutes I spent. So don't feel bad if you can't come up with a solution to this, and we'll see one on the next slide. And if you can, well, you get to feel like you're smarter than me, so that's nice. Okay, so somehow we want to ensure that the sum can't be 0 unless we pick one element from each subarray. So how can we encode that constraint in the problem instance for 3-sum 0? Well, if we multiply all of the array indices by 10, doing so will preserve the set of elements that sum, the sets, of elements that sum to 10, right? If a set of elements sum to 10 before we multiply everything by, sum to 0, if a set of elements summed to 0 before we multiplied everything by 10, then that same set of elements will sum to 0 after we multiplied by 10. Similarly, and conversely, if a set of elements sums to 0 after we multiply everything by 10, that same set of elements already summed to 0 before I multiplied by 10. So this will preserve the sets of elements that sum to 10. But this doesn't guarantee that we can only get 0 if we pick one from each subset. Okay, so we're getting to the point where we're going to pull back the curtain and reveal the magical algorithmic trick that'll accomplish this. So we're going to add 1 to each of the elements of subset A. We're going to add 2 to each of the elements of subset B. And we're going to add -3 or subtract 3 from each of the elements of subset C, of subarray C. Okay, well, I mean, how does that help us? Well, note that A of I mod 10 is 1 for something in the A subarray. So mod 10, it's 1. And A of J, I don't know why I've said, well, this is a poor choice of I shouldn't have used A here. I should have used B. So B of J mod 10. So something in this B subarray is 2 mod 10, right? And then, so really this should be C of K mod 10. So something in this C subarray taken mod 10 is going to be 7. Now, if you think for a moment, if I take a sum of elements, suppose I take 3 elements from A, and mod 10, those elements are all 1. The sum of 3 elements mod 10, if all 3 are from A, will be 3. But, well, if a sum of 3 elements is 0, their sum mod 10 must be 0. So, if we're going to pick 3 elements from this big combined array after this modification, and have their sum be 0, then their sum mod 10 must also be 0, which means I need to be able to add these residuals together and get 0 mod 10. The only way to do that is by taking one element from subarray A, one element from subarray B, and one element from subarray C, because 7 plus 2 plus 1 mod 10 is 0. Now, you can do this checking yourself, but if you just enumerate all of the other cases, there are no other ways to choose elements, to choose 3 elements to get the sum of these residuals to be 0 taken mod 10, right? 1 plus 1 plus 1 is 3, which is 3 mod 10. 1 plus 2 plus 2 is 5. 2 plus 2 plus 2 is 6. 2 plus 1 plus 7. Well, that was good. That's 1 from each. That sums to 10. 7 plus 7 plus 7 is 21, which is 1. 7 and 7 is 14, which is 4. So you can get this idea that the only way to pick elements such that their sums after this transformation, is 0, is to pick one from each of these 3. So these modular residuals sum to 0 taken mod 10. Okay? So that's the magic. And here's how you would implement it. So we'd have reduced 3-array 3sum0 to 3sum0, A, B, C, or your input arrays. We would construct new input arrays, D, E, F, and then we're going to concatenate D, E, F. So for each element of each of these input arrays, we're going to take D to be 10 times A plus 1, E to be 10 times B plus 2, and F to be 10 times C minus 3, right? Just as we showed on the previous slide. We're going to concatenate those 3 subarrays. We get A prime. We're going to call solve 3sum0 on A prime. So is this correct? Well, my claim is that it's correct. Let's show that it's correct. To show that it's correct, we have to prove the following. True is correct for solve 3sum0 A prime. If and only if, so true is correct for this call, if and only if true is the correct output for this whole call, because we return exactly the output of this call. And sorry, my animations are out of order here, but for brevity, let's just call this really long name. Let's just call this solve3 array, okay? So solve3 array, ABC. So we're going to show true is the correct output for solve3sum0, if and only if true is the correct output for solve3 array. Okay, so in other words, by returning the solution to solve 3sum0 as our solution to solve 3 array, we're doing the correct thing. Okay, so that's what we're going to show. And there are 2 cases we're going to run through. So first, assume true is the correct output for solve 3 array. Well, what does that mean? It means, okay, well, sorry, before we ask what that means, if we assume that true is the correct output for solve 3 array, we want to show true is the correct output for solve 3sum0 on the transformed input. So, okay, what does it mean that true is the correct output for solve 3 array? It means by our assumption that true is the correct output, there exist AI plus BJ plus CK that are equal to 0. So if we multiply all 3 of these by 10 and add 1 to AI, 2 to BJ, and subtract 3 from CK, we still get 0. Why? Because these 3 sum to 0, so 10 times these 3 sum to 0, and then adding 1, adding 2, and subtracting 3 sums to 0. So this all still sums to 0. Okay, that's our DI. This is our EJ, and this is our FK. So what this means is we will be able to find 3 elements, DI, EJ, FK, in A prime, that sum to 0. Sorry, I keep advancing animations and slides by accident. Okay, so true is the correct output. There is this DI, EJ, and FK that sum to 0 in the transformed input. So true is the correct output for solve 3sum0. Now let's do the opposite case. Let's suppose true is the correct output for solve 3sum0 and show that true is the correct output for solve 3 array. Well, if true is the correct output for solve 3sum0, that means in this transformed array A prime, a prime of I plus a prime of j plus a prime of k equals 0 for some ijk. Okay? Now the claim is that this sum consists of one or more element from each of A, B, and C. Sorry, not one or more, one element from each of A, B, and C. Okay, and the argument here would be by cases, just as I basically made that argument intuitively a couple slides ago. So as an example case, suppose, to obtain a contradiction, that a prime of I, a prime of j, and a prime of k are all from subarray B. In other words, they were all found in E, the subarray E of a prime. So they all came from the subarray B in the original input. Well then, the sum of those three elements in a prime would be, remember, a prime is obtained by concatenating D, E, and F. And these elements came from B, so they were in E, so they were transformed by multiplying by 10 and adding 2. So that means the sum of these three numbers can be expressed as 10 times B of something plus 2, plus 10 times B of something plus 2, plus 10 times B of something plus 2. So you can see that this is not going to end up being 0, because it's going to be the residuals taken mod 10 are going to be 2 plus 2 plus 2, which is 6. And mod 10, that's still 6, which is not 0. So they cannot sum to 0. So this is a contradiction. So what this means is, if you enumerate all of these different cases, all the ways of choosing three elements from these three different subarrays, D, E, and F, you'll see that there are contradictions in all of those cases except in the case where there's one element from each of A, B, and C. And that will prove this case. That will prove that if there are a prime of I, a prime of j, a prime of k that sum to 0, then there must be three elements chosen, one from each of A, B, and C in the original input that will sum to 0. So there is a sum with one from each of A chosen from one element chosen from each of A, B, and C. So true is the correct output for solve 3 array. Okay, and so if I'm to express this using the notation that we talked about for reductions, 3 array 3 sum 0 reduces to 3 sum 0, or the solution to 3 sum 0 goes as a subproblem into 3 array 3 sum 0's larger solution. Okay, so the previous 3 reductions that we saw all had a very special structure. We transformed or reduced an instance of the first problem to an instance of the subproblem, the second problem. We called the oracle once on the transformed instance. So reductions of this form in the context of decision problems are called many-to-one reductions. These are also known as polynomial transformations or CARP reductions. We call them polynomial transformations because they have this form and they add at most polytime overhead, polynomial overhead. We'll talk more about what that means when we get into really the nitty-gritty of complexity. And we'll see lots of examples of this in the section of the course on intractability. Now the first reduction that I covered in this lecture did not do a single oracle call. It had many oracle calls, so that would not be a many-to-one reduction, and we'll talk more about what kind of reduction that's called a little bit later in the course. Okay, so that's it for the mandatory content for this lecture, and I'll leave you with a random time lapse of stuff that I cobbled together, and I look forward to seeing you guys in the next lecture where we'll talk about divide and conquer. See you guys.